Hi everyone, today we're going to look at the hydration of alkenes in chapter 8. So when we're looking at the hydration of alkenes, what happens is we're going to have the addition of water. The addition of water is going to have an hydrogen atom adding to one carbon and this hydroxy group adding to the other carbon atom. We looked at the reverse process in chapter 7 when we talked about the dehydration of alcohols. So remember we looked at elimination E1 reactions. So we have the alkane, we have our hydroxy and our hydrogen, and when it's in the presence of sulfuric acid with heat, we have our elimination product, which is shown here. So the first type of hydration of alkenes that we're going to look into is we're going to look at the acid catalyzed hydration. So when we talk about the acid catalyzed hydration, this is going to be Markovnikov addition. So remember that Markovnikov addition, that means that our hydroxy group will be adding to the most substituted carbon atom. So again, I'm going to go through the mechanism, make sure that you're understanding the mechanism so that you understand how the products are actually forming. So when we have an acid catalyzed hydration, what happens is we use a strong acid with a non-nucleophile counter anion. So some good examples, sulfuric acid is probably the most common. You'll also see nitric acid or phosphoric acid. What happens is we're going to have protonation of the double bond, and we're going to form a carbocation. Next, we will have the nucleophilic attack by water, and this is going to give us a protonated alcohol. And then the last step we're going to have is we're going to have that deprotonation to give the alcohol. So let's look at an actual mechanism of the acid catalyzed hydration using the Markovnikov addition. So we will have something that looks like this, plus water. So again, we need some strong acid. Typically sulfuric acid will be used, so a catalytical amount. And then what happens is we will have the addition of our hydroxy on our most substituted carbon, which in this case would be this carbon right here. On this carbon here, we would have the addition of our hydrogen. So again, we're going to have that Markovnikov addition. Now let's look at the actual mechanism for this reaction. So when we look at the mechanism, so sulfuric acid is typically shown as H3O plus because remember sulfuric acid dissociates in solution. So it's usually indicated by, again, just showing that hydronium ion. So what will happen is, again, we're going to have protonation of our double bond. So when we have protonation of our double bond, we have the formation of our carbocation. So this is really showing you why you need that Markovnikov addition, right? Because again, we want to have our carbocation on a tertiary carbon, preferably, because we need to make sure that that carbocation is stable. So next, we're going to have the attack of our water onto the carbocation. So we will have the formation of this product here. So our oxygen has a plus formal charge, which we don't want. So what happens is the water is going to deprotonate one of the protons, and this will leave us with our Markovnikov product. So again, the reason behind why the Markovnikov addition happens is because, again, we need to have this carbocation on a preferably tertiary carbon or secondary. We can't put a carbocation on a primary carbon. So let's look at another example. I'm going to kind of scroll all the way down just so I have enough room to write this all the way out. So let's look at this example right here. So we're going to have the addition of water. Again, we're in the presence of a catalytical amount of sulfuric acid. So what would happen is we are going to add our, so we're looking at this carbon and this carbon. So we know that our OH is going to have to go to the most substituted. So OH would go here. Plus we can also have OH behind. So the carbocation, remember, is going to be planar. So we can have both the front side attack and the back side attack of that hydroxy. So let's look at the mechanism for this entire reaction. So again, we have our hydronium. We're going to have protonation of that double bond. We're going to have the formation of our carbocation. So we're on a secondary carbon. Then we are going to have attack of our water molecule onto that carbocation. So we're going to have, I'm just going to show it for the wedge, but it's going to be exactly the same. You would show it for each, both the wedge and the dash. So our oxygen is positive formal charge, which we don't want. Water is going to act as a weak base, deprotonate one of those protons, and we will be left with our product. So there are a lot of side reactions that can actually happen when we look at acid catalyzed hydration. So let's look at some of the side products that we could form. So we have, I'm just going to go from the carbocation. So this generated right here. So we have our carbocation. So one thing that we could do that we learned about is we could have a hydride shift. So a hydride shift is likely to happen because we're going to go from a secondary carbon to a tertiary carbon. So it's going to be a more stable carbocation. Then what would happen is we would have attack of our water molecule. Sorry about that. And then we can have deprotonation of the proton, and we would be left with our substitution product right here. Again, substitution product. We would have stereochemistry that we would have to show because this carbon is a stereocenter. Another possibility is we have this carbocation that we're starting with. We could have the elimination product. So we could have this product shown here. We could look at this carbocation from our hydride shift, and we could have another elimination product, which is shown here. So direct hydration, which we're just talking about right now with this Markovnikov addition with the acid catalyzed hydration, is usually impractical. And the reasons that it's impractical is because most alkenes, first of all, are going to be insoluble in water. And then second problem that we have, which we just looked at when we looked at the side products, is that we have the possibility of carbocation rearrangements. So since this isn't the ideal way to do hydration of alkenes, we're going to talk about some reactions that we can control a little bit better when we're doing Markovnikov addition. So these types of reactions are going to be called oxymercuration, demercuration. So again, this is going to be Markovnikov addition. So Markovnikov, automatically think the hydroxy is going to go to the most substituted carbon atom. So again, oxymercuration, demercuration is used as an alternative to the direct addition of water, which is what we just looked at. So we have to think about two advantages that we have. So two of the most significant advantages, I should say. So the first advantage of using this oxymercuration, demercuration is going to be that we suppress that carbocation rearrangement. So we're going to look at a more stable intermediate that we can form. And secondly, we are using milder conditions. So you have to think in the direct hydration of alkenes, we're using strong acids. So when we look at the oxymercuration, demercuration, we have much milder conditions. So this is going to be a two-step process. The first step is going to be oxymercuration. So what happens is in this step is we're going to add mercury and oxygen across the double bond. This is going to be Markovnikov and anti-addition. So remember, anti means one would be the dash and one would be the wedge. So one's coming out, one's going in. And then our second step is going to be the demercuration. So when we look at demercuration, what happens here is we're going to replace the mercury with a hydrogen in this reduction process. So let's look at an example. So we're just going to look at the products first, and then I'll walk you through the mechanism for the oxymercuration step. And then for the demercurization step, we actually don't cover the mechanism. So it's not something that we're just not covering this semester. We don't typically cover it in Organic 1 at all. So when we look at our first example, we have this alkene. We're going to have mercury acetate in water. So you'll notice that I'm circling the numbers 1 and 2. So this is typical when you're indicating that you have more than one step process. So previously we would just add reactants or reagents over the arrow and not specifically show number 1, number 2, and that just means that it's not a 2-step process, for example. So in this case, we're showing mercury acetate in water for our first step, and then we have sodium borohydride and sodium hydroxide. So what happens here is we're going to form that Markovnikov product. So we're looking at this double bond here. So hydrogen is going to go to the least substituted, and our hydroxy is going to go to the more substituted carbon. So again, this is going to be Markovnikov addition, and we have no rearrangement, no elimination reactions. So again, this is why these reactions are preferred over the other hydration that we looked at of alkenes in the beginning of this lecture. So let's look at the mechanism for this reaction. So when we look at the mechanism, so we're looking at the mechanism specifically right now for the oxymercuration. So what happens, or what is believed to happen, is our mercury acetate is believed to dissociate in solution. So it's believed to break apart in solution. So what happens is we're going to have this plus our acetate. So remember that acetate is, so O minus AC is equal to, just in case you don't remember what the acetate ion is. So let's look at the mechanism for this. So what we're going to take is we're going to take this product right here from the dissociation of that mercury to acetate. So what happens is we're going to have, oh, sorry, sometimes this program likes to do its own thing. Again. All right, so we have our alkene. We're going to have our mercury acetate. So this is going to be our electrophile. I'll just put E for electrophile. We're going to form this 3-membered ring. So what happens when we form this? I'm going to kind of walk you through. So we're going to have something that looks like this. We have our mercury is going to be partially positive, which we're going to talk about. So this intermediate here is called the mercranium ion. So this is possible because the D electrons on the mercury are donated to form this 3-membered ring, or this bridge species. Again, the positive charge is going to be put on the mercury ion, which is shown here. But what also happens is this positive charge is going to actually be spread over all 3 of the atoms in the 3-membered ring. So we have it on mercury, we have it on this carbon, and we have it on this carbon. But for the 2 carbons, when we look at the difference between them, the greater positive charge is going to be on the more stable carbon. The more stable carbon is going to be the more substituted carbon, which in this case would be this carbon right here. So again, this is going to be greater partial positive charge. So this is important because this allows us to know where our water is going to attack. So water is going to attack fastest at the carbon with the more positive charge density. So again, this is going to be the more substituted carbon. So what's going to happen is that the water is going to come in and kind of break this 3-membered ring. So again, it's going to attack this carbon because it's the more stable carbon. And this bond right here that I kind of just scribbled out is going to break. So what's going to happen is we are going to have this product right here. Our acetate ion will deprotonate this, and we will be left with this product right here. So again, water is going to attack at the more substituted carbon because it has a greater positive charge density. And since the mercury bond is intact when the attack occurs, the water must attack from backside. And this is why that anti-addition is coming into play. So let's look at the nature of that mercurium ion. So we're going to look at it a little bit slower. So I mentioned a lot of the things that I will right now, but we're gonna, again, just look at it a little bit more stepwise. So if we look at this mercurium ion, what happens is if we break A or break B, so I'll call this one A, I'll call this one B. So if we break bond A, what happens is we're gonna have our carbocation on a primary carbon, which we know that that's not going to be stable. If we break bond B, we're going to make a more stable carbocation. So in this case, we're going to put our carbocation on a secondary carbon. So this is the real reason why, again, we're going to always have an attack of our water on the more substituted, again, because then we're putting that carbocation also on something that is secondary or tertiary, for example. If we look at this right here, so again, we have our mercury ion. We're going to form that 3-membered ring. So if you were asked to draw the mechanism for a reaction, this would be expected for oxymercuration, for example. So again, we have partial positive charge spread out throughout that 3-membered ring. This carbon is going to have a greater partial positive charge than this carbon here, just because it's substituted, so it's more stable. And then when we have the addition or attack of our water, we're going to have the attack of our water on the back side, again, because the mercury, right, is still intact. So in order for the water to come in, it has to go on the back side. And then we have deprotonation of our proton here by that acetate ligand, or acetate ion, I should say. So the next step that we're going to look at, demercuration. So with demercuration, this is again that second step where we use that sodium borohydride. If we have this product from our second step, we use sodium borohydride and sodium hydroxide. And what happens in this second step is that we have a reduction process. So we're going to replace the mercury with a proton. So the sodium borohydride, that NaBH4, is going to act as the source of the hydride. So what the product will look like will just be this shown here. So again, this hydrogen is just replacing the mercury. So again, we won't be covering the mechanism for demercuration, so it's not something that you will have to know for the exam, but if you were asked a mechanism, you should know how to work all the way through that oxymercuration step. So next we're going to look at the stereochemistry for these reactions. So when we look at the stereochemistry, let's start with this alkene right here. So we're going to have this bulky tert butyl group, which is going to be important to think about. And we have the mercury acetate. So again, we're going to form that 3-membered ring. So when we have the attack, how is mercury going to add is something we have to think about. So in this case, we're going to have it adding to the behind or into the screen. So think about why that would happen, right? So we have this bulky tert butyl group here. So really, because of that bulky tert butyl group, the backside attack is the most likely, just because it's going to be the less hindered face. So when we have that backside attack of our mercury, we have this methyl group here. So this methyl group here is right here. And then what's going to happen is we're going to have the attack of our water molecule. So the water molecule, again, is going to be attacking on our more substituted. So it's going to attack right here. We're going to have the, so tert-butyl stereochemistry staying the same. Our mercury is also staying the same. So as this bond is breaking right here, the mercury is still staying behind the computer or paper. And then we're going to have anti-addition of our water molecule. So remember, this has to be anti-addition because we have this bond right here is still intact. So as that's breaking, the water's coming into attack. So we have to have that backside attack. So now our methyl group is going to be behind the page. And then we're going to have water, or your acetate can deprotonate this proton here, and you will be left with your product from your first step. So product from the first step is going to look like this. So again, there's a lot to think about. So that initial attack of that mercury acetate is going to occur on the bottom or the backside of the alkene because it's going to be opposite of that bulky tert-butyl group, which is going to be the less hindered face in this case. And then our attack of the water onto that mercanium ion must occur from the backside of that carbon-mercury bond. So the hydroxy or OH in the final products ends up being facing the more hindered face. But again, that's just because we have to have that anti-addition. When we look at the stereochemistry in the second step, so that demercuration step, so the stereochemistry in second step results in the loss of actually stereochemistry. So let's look at a product from the first step. So if we had this product here, I've actually had a lot of people ask this. So D is deuterium, just the isotope of hydrogen. So it's just indicating that that would be a stereocenter. So again, second step, we have sodium borohydride and sodium hydroxide. So the products, what they're going to be, so at this stereocenter right here, it's going to stay the same. So we're not losing our stereochemistry there. But what happens is that we're going to have a loss of stereochemistry in this position here. So we can have this product here, plus we can have this product here. So again, in this position or at that stereo center, that's where we're having the loss of that stereochemistry. So this, of course, is only if mercury is attached to a chiral center. Then the established stereochemistry would be lost. If it's not a stereo center or a chiral center, then you don't have to worry about the stereochemistry anyways. So let's look at the last reaction for today's lecture. Again, there's a lot of reactions in chapter 8, so just try your best to stay on top of them. If you have questions, I recommend reaching out sooner than later, just because we're going to have a lot more on the next lecture also. All right, so now we're going to talk about the alkoxymercuration demercuration. So this is going to be the same idea, except instead of using water, we're going to use an alcohol. So we're going to use methanol in this example here. So if we have this alkene here, we have a reaction showing methanol and our mercury acetate. So again, instead of using water, we're substituting for methanol. And then our second step is going to be that sodium borohydride in sodium hydroxide. So what would happen is we're going to have the formation of this product here. So what's going to happen is kind of what we looked at in SN1 reactions. Remember when we have methanol, so CH3OH, it's going to result in the addition of that OCH3. So let's look at the mechanism for this so you can see how that OCH3 is being added. So what will happen is we're going to have this right here, right? And then we're going to form our mercury kind of three-membered ring here. So what will happen now is this bond right here is going to break. we have a greater positive charge on this carbon here. So we're going to have attack of our methanol in this case. When we have attack of that methanol, again, oxygen is going to have that plus formal charge. So our acetate ion will deprotonate that proton, and we would be left with this product right here. And then what will happen is we have our second step, so that's sodium borohydride and sodium hydroxide. And again, this is the reduction process where we're just replacing our mercury with a hydrogen. Oops, sorry, me. So again, you don't really have to show this bond, but we're replacing this entire mercury with a hydrogen in that second demercuration step. So again, it's really the same idea, except instead of adding water to it, we're just adding that methanol. So we call it alkoxymercuration instead of oxymercuration. So same idea is that the attack of the alcohol or the methanol has to be on the greater positive charge density carbon atom, which is just going to be the more substituted. So attack of that molecule will result in the alcohol being on the more substituted. And then in that second step, the mercury is just going to be replaced with or reduced with 2 hydrogen. So if you have any questions, I recommend practicing the ones in the book, working on any drill problems from our section, from Professor Rosenstein, from Professor Madrix, and then reach out to me with any questions that you guys may have. Try to understand the oxymercuration, demercuration, or alkoxymercuration, demercuration before you start the material on the next lecture. I hope everyone's doing well and everyone has a great day.